Welcome everyone to the Berlin Functional Programming Group. Tonight we have Christoph Hegemann live from the other side of Germany, from Berlin, to present us with his exciting workshop, Type Inference from Scratch. And my understanding is if you don't know anything about the classic type inference algorithm, you are going to understand it by the end of this workshop, and it is not as scary as you may think. I would like this to be the message of all of functional programming, right? It's not as scary as you think. In fact, a lot of it makes sense, and you can walk through functional programming step by step and actually come to an understanding of it and develop a transferable set of ideas that works across functional programming languages. I mean, I think that is the ideal. I think this is one of the things that appeals to me about functional programming and probably a lot of people. Not its complexity, but actually its simplicity. But apparently you have to have a certain kind of mind for it. And that's why I'm doing these meetups so that we can gather people who are of this mindset together and share ideas and learn. Christoph loves teaching, and I think you're going to enjoy learning from him. What can I say about Christoph by way of introduction? He likes working on compilers. He's contributed a lot to PureScript and some kind of programming language called Motoko, which I've never heard of, but maybe he'll explain. And some of his ideas have also been integrated into the GHC Haskell compiler, which I can't help but respect. So I think it's going to be a pretty in-depth workshop, and it's going to be interactive. I hope you're prepared to code. And take it away, Christoph.
Thank you, Stephen, for the lovely introduction. Yeah, exactly. We're trying to understand type inference today. And it's not only that it's not that hard to understand or that there's that it's possible to understand for everyone. It's also that we can understand it as just a program or via programming. It doesn't always have to be all this like theory heavy stuff. We don't always have to start with the theory. We can kind of find a way into the theory from the programming side as well. All right, so I am going to share my screen then. And I hope everyone can see this. So let's start at the start. All right, so one more time, welcome everyone. This is a workshop. So we'll have you set up the development environment, or I hope you've already set it up. If you don't, these are the two things you'll need to have installed by the time it gets to you coding, which is a few minutes from now. So if you haven't, you've still got time. You'll need Git and IntelliJ, and I'm going to show you how to set this up. Yeah, and if you've got any questions or anything in between, just let me know, and I will be happy to answer right away. I won't be able to follow the chat though, so just shout it in there, I guess. So I want to start up by just giving us, well, we've heard the name type inference a few times now, but we are going to look at the definition from Wikipedia here because I think it's a good one. So on Wikipedia is defined as type inference being refers to the automatic detection of the type of an expression in a programming language. That's a mouthful, but there's 4 important bits here. There are expressions in a programming language. So we're going to need a programming language with expressions. And then we are going to have types, which correspond to these expressions. And then the algorithm we'll be implementing is the detection part. All right. And so the way we're going to do that is that first I'm going to show you the programming language, which means I'm going to also show you the expressions. And for that, I have a few example programs. And then we're going to look at how these programs end up being represented as data, because a compiler or a type inferencer or type checker in our case is just a program, and programs operate on data. So what we do need is a way to represent programs as data. And that's commonly referred to as abstract syntax. And we're going to look at how that is defined. And we're going to get our first look at some of the Kotlin syntax you'll be using. And then we're just going to get into the coding, really, where we'll be alternating between mop programming, which means I'm the one coding, but I'm just typing and you're telling me what to code. And pair programming, by which we're going to define pair to be a larger group than 2 this time around, because this is a remote workshop now, and so we kind of need to adapt. Any questions at this point in time? If not, I'm just going to get into the setting up part. All right, good. So for setting up, what you need to do is you need to clone the repo at this URL. I'm sure it's also in the mention on the meetup page, so you can also find it there. And then you need to open the project in IntelliJ, which is the IDE that we're going to be using. And it should be recognized as a Gradle project. What that means, I'll show you in a second. And then if everything works, you should be able to run the examples. All right, so what I have here is a fresh checkout of the aforementioned repo. I have just freshly cloned this, so I have not opened this up in the IDE yet. So when you start IntelliJ for the first time, what you're going to get is a window like this. And if you've already started before and you maybe have some project open, what you need to do is you need to click on File and Close Project to get into this state. All right. And then what you're going to do is you're going to click Open or Import. And we're going to, and then we're going to find the place where we did the checkout, which is over here for me. So this is the info workshop directory. And I'm going to say OK. And you can see in the bottom right, this is the dialog that's relevant, where it says import Gradle project. And I'm going to click on this import Gradle project bit, and that's going to make the IDE spin a bit in the background while it's downloading the dependencies and finishing the first build. So if you follow all of those steps, you should be good to go. And I'm hoping that all or most of you can get this far by the time that we need to write some code. If any of you haven't, though, we can totally look at this together. All right. So I said that the next thing we're going to do is we're going to look at the examples task. And you can see up here, there's a bunch of tasks here. And we'll look at what these mean or what these are supposed to do. See up here. But I'm going to click on the examples one. And that corresponds to a file called examples. A file main in the examples directory over here. And what we can do is we can run this by clicking the run button up there. And the first time around is going to take a bit because it's going to build. But now you see that it produced a bunch of output. And this is the 99 bottles of beer song that it's outputting there, which is kind of noisy. So I'm going to mute that for now. Really, the main purpose of that exercise is to show you that this is a proper programming language. I'm going to run this thing again, and you can see that we have a bunch of examples here. So what this project comes with is a parser and an interpreter for this language, which is an ML-like, you could say. It's a very simple programming language, a very simple functional programming language. And it's also, I think it also contains a pretty printer. The part we're going to be filling in is the type checker, but all the other stuff is there so that we can make sure that we can run this stuff and get an understanding and have like a little bit of a more pleasant way of interacting with this programming language. Okay, so our programming language, these are a few expressions in it. Our programming language has ints. Okay, and so we can write these as 1, or I could write 12. And as you can see over here, integers, when I evaluate them, they're just constants, right? So they return themselves essentially. We have Booleans in our programming language, and Booleans are relevant because we also have if statements, which we'll see in a second, and we have string literals. So here you see I'm using a bit of Kotlin syntax that you might want to get used to. It's the triple triple quote, which means that everything in here is a string that I do not no longer need to escape, which is kind of nice when you're writing larger programs that contain characters that you'd usually need to escape. Okay, so we've got ints, bools, and strings. That's our three primitive data types, and you can see that we can execute or like evaluate all of them, and they just stay constant. So the next thing we have is variables. And if I just say, well, if I just try to evaluate a naked variable like this, what's actually going to happen is that the execution is going to fail, and it's going to tell me that there's an unknown variable x over here. So how do we bring variables into scope then? And that's using, we're going to do that through the let construct. So what this means, right? So let x equals 10 in x. That's the expression here. And you see, I've got it formatted a little weird over here. The Haskellers will find this especially weird. The OCamlers or like SML people won't. But really, what you can read this in as, you can think of it as a semicolon if you're coming from any of the more imperative programming languages or any of the more C-style syntax languages, really. So what we're saying here is that x equals 10, and then we're using x, which gives us, which returns just the number 10, right? And then the next thing we have is lambdas. So lambdas are the second way of bringing variables into scope in our programming language. And what I have here is a lambda, or an anonymous function, which binds an argument or takes an argument and calls it x, and then the body over here, that it just returns that x back. And over here, don't worry about this too much, but basically at runtime, our lambdas are closures. And so just evaluating a lambda is a closure value. And what we can do with these closures, or these lambdas really, is we can apply them to arguments. This is what makes this thing a functional programming language, essentially. Okay, so here now we're taking the identity function that we've defined up here, and we're applying it to a string. And what we get back, which is this part, we just get back the string hello. All right, so function application is just juxtaposition, right? So we put a space in between. The ones of you that have done some Haskell before, or Elm or PureScript, are used to this kind of function application style, but it takes some use. If you're not, basically, well, a space between two expressions means the thing on the left is a function being applied to the thing on the right. Now we have Booleans. And if we want to make use of those, we've also got an if statement in our language. This is really crucial so that we can terminate recursion for us, for our examples, but it's also just a nice usage of bools. So here we have huge if true, and you can see that that's huge. And we could also try huge if true on false, and you can see that that is going to return small. Okay. Okay. There are things we can write in our language that the interpreter is just going to accept, right? We haven't implemented the type checker, so far this interpreter is essentially JavaScript. You can see that this thing just returns 20 because this is false, and so it evaluates the else branch. But this is not a well-typed expression because depending on what this Boolean is, it's going to give us either a string or an int. Well, it's not a well-typed expression in our language anyway. We don't have our types depend on values. Sorry, just need to let my cat out. All right. Questions up to this point?
Are we going to have typing expressions, or can we say a variable has a specific type, or is that not going to happen?
I don't think we have annotations in here yet. We could add them if we wanted to, and some of the code is there, but I don't think we'll have those expressions in here because we can't, because the algorithm we're going to be implementing can't really make use of it. If you want to stick around afterwards for a bit, I can definitely show you how we do that, though, if you're interested. Okay.
Do we have recursive functions?
Yes, I'll show you in a bit. All right.
Is the
So,
language going to be total if we have recursion?
well, no, it's not. Actually, I think a recursion is, now we have recursion. Yeah, the language is not total. This is basically SML without modules. Okay. So what I'm going to do now is I'm going to show a few more examples that put together some of the features I just talked about, so we get an idea of what programming in this programming language looks like. Okay. So here I'm let binding a value and call it identity, and that value is the lambda we've seen before, the identity function. And then over here I'm applying it to a string hello friends, and over here you can see that the result of that is just hello friends. So functions are just values, right? We can bind those to any name we'd like, and we can pass them around as arguments, which I'm going to show you in a second. Here we have, this example is already called currying one. So all our functions take exactly one argument. And if we want to build a function that takes two, like say the const function, which takes two arguments and always returns its first, we need to nest these lambdas. So this is what that looks like. So basically we make a function that takes an x, and then it returns a function itself, which takes the next argument, and then it returns the value x. And I just put these parentheses in there to explain how the precedence works out in the parser, but we don't need to write those down. So implicitly, this means, well, there's really no other way of bracketing this up, but if you see this means that there's parentheses around here, basically. Okay. And then again, I can apply just a single argument here, and you can see that this returns a closure again, because this is just basically returning this value, right? And then if we apply the second argument, what we get back is the integer 10, because that's what we bound to x earlier. Okay. And so now the last thing I want to show you is higher order programming, higher order. I'm using higher order functions here, really. So this is the flip function. This might look a little weird. It's a function that takes 3 arguments, and then it basically swaps around the last 2, and the first argument we get is a function. Okay. So if you remember up here, when we applied const to 10 and hello friends, it returned 10. But now what we're going to do is we're going to flip const around. So flip is a function that takes another function as an argument, right? This is what makes this a functional programming language. And as you can see down here, that returns hello friends. So it does not return 10 because it's flipped around these 2 arguments. Okay. And then I can show that we have, well, the hello world of programming languages, really, we can implement the Fibonacci function by using a couple of built-ins. So I have an equality function for int, and an addition function, a subtraction function that already exists in the interpreter, essentially. And, well, I can compute the 15th Fibonacci number, which is 15, which is 610, so that works fine. So this is what we can tell that this is, the interpreter knows how to do recursive let bindings. Okay. And the last example is, as I said, the 99 bottles example, and you can look at that yourself if you want. Really, this is just to show that this is a programming language you can use to mess around if you want to. Okay. So this is what that outputs, right? So we have strings and we can concatenate them, apparently, basically. That's our programming language. Are there any more questions at this point in time? Really, we'll get to know this programming language a bit more. We'll look at each construction individually when we think about how to type them, but it's still good to have an intuition for the programming language we're going to be working with here. Okay, that looks good. In that case, the next thing I want to show you is the syntax/AST file. Okay. And so this is where all of the constructions that I've just shown you are defined in Kotlin. So this is what the abstract syntax looks like. Okay, this is the data type for this. And if you come from Haskell or any of those languages, this is basically a giant ADT. Well, it's not giant, but it's an ADT. This is just how we represent these in Kotlin. Okay. And so we have, as we said before, ints and bools, and we have strings. Those three are literals, and they just contain, well, the Kotlin equivalent of what they represent. And then we have variables, which every variable has a name, which really is just a new type wrapper on the string. We have let bindings, which have a name, an expression that they bind to that name, and a body. Well, and lambdas and applications and divs, really. When you're solving the tasks, I'm going to be giving you, you're going to need to look at this file, or you're going to want to look at this file to look at the type definition of these things. When you're in IntelliJ, what you can do is you can press Control and click on any name, really, and it's going to take you to the definition of that name. Okay, so that's a useful thing to know. Right. More orientation. The only file you'll need to edit in order to solve all the tasks I'm going to be giving you is the typechecker.kt file underneath the types subdirectory. Okay. Or it contains a bit of code and a few to-dos. And so I'm going to go over what these things mean, but this is the class, or this is the type checker that will contain all the logic. Okay, and we're going to look at all these things when the time comes. All right, so I think the last thing we need to look at, or we need to understand, is our type language. And once we're done that, we should be good to go with the whole type checking thing. So let's look at that one more time. The AST file again, and there's a type called monotype in here. The reason is that we're not going to be doing polymorphism today, I don't think, unless we find that we're super quick and have a lot of time at the end, then we can do some polymorphism. Okay. And the way our types are defined is that we have three primitive types. We have int, string, and bool, which correspond to the literals that we have in our expression language. And then we have, most importantly, the function type, which is a type that has an argument and a result type. And we write that like so. So I can say int to int. That's a function that takes an int and returns an int. And I can say int to bool to int like so. Right? And what that means is that I'm going to add the brackets here again, the parentheses, right? So this is a function that takes an int of type. This is a function that takes an int as a parameter and then returns another function which takes a Boolean as a parameter and then returns an integer, okay? And the thing that's confusing about that for some of you is that if I write out fxy as an expression in our programming language, that really means that we apply f to x and then return the results to y, right? So this is left associative. And if I say int string to int or something, that's right associative. So this sometimes trips people up. So try to keep that in mind when you look at expressions and types. Okay. All right. So I'd say let's get started. The way this is going to work is that we are going to solve 1 through 8. of these tasks. And you're going to be starting with 1. I will do one of these cases, and then you're going to do the others. And then I'm going to do let together with you, and then you're going to do 3 and so forth. Okay. And so let's start with 1. So what does that mean? That means that we are going to go up here, see these run configurations, and we're going to pick the literal and var configuration because that's the one we're supposed to be solving. And I'm going to increase the size of it just a little bit. So let's go for 22 maybe. Okay. Okay, and so I've selected this up here, and now I'm going to hit run. And what this is going to do is this is going to run a bunch of unit tests. And as we see right now, 5 of these tests, 5 of the 5 tests I've run have failed. And our job now is to make all of these tests pass. Okay. And so we are going to, we can double click on these tests down here in the bottom, and it takes us to their definition. Now the order here is a little strange sometimes, but really what you want to be looking for is the definition in the test file, the order in the test file. And so the first test we're going to try to make green is this one. Okay, and so what this test says is it infers the type of an int literal. So the expression 42 is supposed to have the type int. Okay. And what we can do here now is I can run this test on its own by clicking on this little icon over here. All right. And so we can see that this test still fails. Well, and now let's try to see where we might go about fixing this. And I already know we want to be looking at the infer function. This is the one where the most of the code is going to go into, and this is the one where we're going to start. So what I'm going to do is I'm going to set a breakpoint in here. Okay. And I am going to go over here one more time, and I'm going to this time around debug this test. Okay. And you can see that the IDE has stopped, the execution has stopped here, and we can see all the variables that are in scope, right? And we can see that the expression over here is an int. What we're supposed to return is a type. So what I'm going to do here is I'm going to say, all right, I know what to do. I'm going to say if the expression, and I'm going to use is here, which is basically how you do pattern matching, is an integer, I'm going to return the int type, and otherwise I'm going to continue failing like so. All right. And so now I can rerun this test. So I'm going to go into the tests again. I'm going to run this test one more time. And as we see, now this test is green and this passes. All right. And so what you're going to be doing is you're going to be inferring the types for literals and variables. So let's think about this just for a quick second before I let you get started. So, well, if I give you an expression that is an int, right, just an integer expression, well, that's always going to have the type int. Okay. And the same thing is going to happen really if I give you a Boolean expression. That's always going to have type bool. And not surprising if I'm going to give you a string. And again, this is representative for all of the strings we can write. This has the type string. Okay. And now the question here is, what is the type for a variable? What's the type of x? Well, we can't tell, right? That depends. What's the type of this? Well, that depends of what context we're looking at this, right? If I said let x equals 10, in something over here, right, in x like so, well, that x is going to have type int. But if I were to say, well, x is equal to the empty string, that x is going to have type string. And the way we represent this is that we say there's an environment. Okay, so environment. And I'm going to put this up here. So environments. Environments. Okay, we write those with capital Greek letters. So this is gamma, which, well, G and K is not that far apart. And so this is the context or the environment in our case, right? And an environment consists of a bunch of variable names and their types. So it's a mapping from variables to types. So the environment might have information that x is an int and y is a bool, and add is a function from int to int to int. Okay. And in our type checker, you have access to that environment through this variable over here. Okay. And so the way we write this is, so x has type t, but x only has type t in a given environment gamma. And this is the syntax for that. And then we're going to write a line up here. Oops. And what that line means is that in order for the things below the line to be true, we need the thing above the line to be true, really. And so we need x has type t to be an element of this gamma. I'm going to show you more of these rules, but really the thing underneath the line, that's the thing we want to show. And in order for that, for us to be able to show that, we need to show that the thing above the line is true. Okay, and that's what you're going to do in the first task, which is implementing type inference for literals and variables. All right, now, can we get a few breakout rooms for these people? Can we manage that? If we can't, I'm gonna let. If we're gonna, I'm gonna have to do this with mob programming, and then you'll have to talk to me so that I can implement stuff.
Do you have the breakout rooms option, or only me?
I think it's only you, unfortunately.
Yep. What do you need?
How many people are we now? Still 30 people. That's a surprise.
Yep.
I don't know. How about let's do 6, and then people can just join join one of those. Really, try to make even groups. But if there's someone you already know and you want to program with, just go together, I'd say.
So this lets me do it automatically or manually.
I mean, if we've yeah, that's a. I mean, we could do it automatically.
I don't know if it's possible for people to like hop around.
Unfortunately, only if you make them co-hosts, but I guess it's not the plan really. So, they can leave, like they can come back into the general channel from their rooms, but they can't move around in them. So, I mean, if there are people that already know that they want to be working together with someone, you can move them around and reassign them. So maybe those people.
We can try and see how it goes. So
Let's just try.
Shall I just do it?
Yeah, let's just try for the first exercise, and if we find that things aren't working, we'll mix it up.
Here we go. Oh, it looks like I can actually manually swap people around here. Mm-hmm. So now's your chance if you want to put this into. Oh wait, we're getting some chat comments. I'm just watching while working, so don't put me in a group. Yeah,
that's why we have 5 people, right?
Yeah, so if some of you end up in a group, I think you can simultaneously be in this like the main meeting and the breakout room at the same time, right?
Yeah, you can swap around between them freely. Once you're assigned, you can swap around at least.
Okay, so let me maybe what I can do is move the people who are just listening into their own group. But it will take me a second.
Yeah, no worries. I'll just leave this up so that people can look at it maybe.
Someone
You
is
might need to make a
asking, someone's asking, where's the repo?
Where's the repo? So it's linked on the meetup page really, but it's also here. So it's critscreek/infer_workshop. I don't know if I can increase the size of that. Well, I can increase the size of this at least. I was hoping you would have done the installing the repo part before we got to the coding.
Have you worked with developers before?
Oh yeah, unfortunately.
Okay.
I mean, someone from the 5-person group might have set it up.
Okay,
There's
this looks, yeah, let's hope so. Okay, so I have some groups of 5 and then a group with, well, actually, I think someone just dropped out. Let's see. Okay. And Joel's in his own group. So when I click open all rooms, the magic should just happen, right?
Yeah.
Okay.
Right. Someone assigned me to a breakout room and my alter ego as well. I'm probably not going to join that. I'm going to wait around here. So if you have any questions, just come into general and I'm happy to help, I guess.
I have some unassigned people. So I'll just, okay, randomly do that. This is interesting. It's sort of hard to experiment with this in advance, right?
Yeah, it really is. You need a certain people count to try and do this. So. Is everyone still here? Did they?
A question in chat. Someone is running Gradle tests from the command line without IntelliJ. Does anyone know a quick command to run a single test?
No clue.
Okay, so it looks like this should be working, right?
I hope so. I think we're not that many people anymore in the main room, at least.
You scared a few off. There are 11 participants here. So are they here and there at the same time? Can they hear us?
No. I mean, if they can hear us, yes, but they're not in their groups if they're here, basically.
Okay.
Yeah, just so you know, I just went back to the main room because I'm just listening. So anyway.
All right, sure. Let's just hope that there's no group. Like if anyone is in a group where there's no one hacking or if they're just alone, let's shuffle them around maybe.
Yeah, so Trevor says that when he joined the breakout room, it muted and hid the main meeting.
Mm-hmm.
Is that intentional?
Yeah, basically it's got basically the general room. Like once they're in their own rooms, they can hopefully also do sharing with one another. I'm not. Oh wait, maybe they can't, right?
That I don't know.
Because you disabled that for the group, right?
Screen sharing?
Or is that allowed for everyone? But
no.
All right, I see. It looked like I was able to share my screen. Okay, that's good.
Yeah,
that's good to know.
Okay.
That's great then. I mean, the recording is just going to be weird, but that's what it is.
Yeah, so
we should have said it's 10 minutes, but I think you can force everyone back.
Do they know what they're supposed to be doing?
I think so. I told them to do the first group of tests, which is... It's not that hard, but people are coming back already.
So while we're waiting, why did you choose Kotlin for this workshop?
Well, really, it's kind of a balanced thing in the sense that the people that, I mean, what are the alternatives, right? You could, of course, do it in a functional programming language, like let's say Haskell or one of those, right? But I'd say the group of people that know Haskell are much more likely to have already had some experience with type inference. And so all of the other people, for them, they're probably less used to this like ML-ish syntax and the type inference part, but they might already be used to Kotlin-like languages. So it's kind of a fair trade-off to not put anyone at everyone at a disadvantage, or anyone. And I mean, the main selling point for me is that I have this IDE that I can like designate testing groups, and you get this like nice breakpoint kind of thing. And you just don't have that in Haskell, and so I think it's very valuable to have easy navigation and breakpoints when you're trying to understand what a program does.
Are you working with Kotlin day to day?
No, I use it just for teaching, really.
Okay.
Day to day is OCaml, but I wouldn't wish that on anyone. So,
Not a fan?
not at all. Consider OCaml a toy.
You can come join me in my new Python world.
Machine learning.
Data science.
Ooh, yes. Which is a fancy word for, I don't know.
It's very interesting, but the application building part is a bit tedious.
All right. Yeah.
And it's very OOP.
Yeah. Yes. Was it TensorFlow and?
I don't know if they're using that. I don't know if they're that advanced. Lots of statistical things, though, for sure.
Sorry, just a question, because when we were split into breakout rooms, I think we lost you. I mean, we didn't hear you, so no idea what we should do, actually.
All right, well, you should try to make the test group, the literal and var test group green, basically, which is the...
Okay.
Right? That's the
Okay.
test you need to be making green.
Okay, and when we come back to the main room,
Well,
it's like when it's finished, or because we'll probably not hear you when you will start again talking.
Right. I mean, when I start with the talking about the solution with everyone together, by then we'll just stop the breakout rooms and get everyone back here.
Cool. Okay.
Right. But
okay.
but if you're done, you're free to come over here and discuss the solution with others.
Yeah, sure. Okay. Thanks.
Cool. Yeah. Should have maybe set that in advance, but that's what you get when you do it for the first time.
Cool. I'll tell people they can rejoin anytime.
Mm-hmm. There's no giving up. When did we start? Oh, let's give him 5 more minutes, maybe. I mean, for the programming part for this exercise, it's like 3 to 4 lines. The first one is like small on purpose so that people can make sure that they have the setup, and like most of the time is spent on the setup in the first task, I guess.
I think if you've been doing this kind of thing for a while, you will get a sense for what works and what doesn't.
Yeah. I mean, it's a lot easier to get just visual cues if you look at a group of people.
Yeah. Yeah, this is really tough what we're doing, but that's why it's experimental.
Right. I mean,
it's not the kind of thing I ever hoped to become good at, but if we keep doing it for another 6 months, I guess we have no choice.
Yeah. I mean,
I just started a new job at a company that I haven't been able to visit in person. I haven't met my team. I can't make eye contact with anybody, so it's very hard to develop relationships. You can, yes. But you have to work harder to do it, I think.
Yes, absolutely. It's I mean, I've been a remote worker for 3 to 4 years now, but still the important bit is the few meetings you have where you meet each other, and then you can go your ways again, but you've met in person before.
I don't think it's about remote work. I think it's about remote culture. My company is not a remote work culture, so
yeah, okay,
it's hard hard to adapt. Like hybrid, I think doesn't work very well. One or the other completely, if you embrace it, can work. I mean, obviously in person is typical.
Yeah. I mean, yeah. Twitter announced that no one needs to come back afterwards. They're like, everyone is free to be a remote worker if they want to.
Right. They don't have to come back ever.
Yeah.
It's brilliant.
Yeah.
I mean, my company, I think they should just sell the building.
Save some money.
Exactly. What's the point?
Yeah.
Christoph, what company are you working with? Or are you working in the company at all?
Yeah, I'm working at DFINITY, which is we're building the internet computer, which is
the internet computer.
Yeah. Amazon Web Services, but blockchain.
Okay.
When's it coming out?
Well, we're working on something that, well, it's already public in the sense that we've demoed it, but the next release in, I think, a month or so is the first one where we let external people run applications on it. So
I got a very cool DFINITY t-shirt from ZuriHack a couple years ago, and so far that's my only exposure to your company's work. Yeah,
we used to be a Haskell shop, but then they switched everything to Rust.
Oh.
Except for the compiler that I'm working on, which is OCaml.
And what is this language? Motoko?
That's Motoko. That's the language we're building, essentially, right?
That's your internal language.
That's the language we're developing. I mean, it compiles to. It's an object-oriented language, I'd say, or like a hybrid, like the model languages, all of them are. But the defining feature is that it compiles to WASM really neatly, because the whole thing runs on WASM. So, or like, the idea is that everything is WASM. So. And
is that why you need a new language?
Yeah, because there's really no high-level language you can compile to WebAssembly at this point in time that doesn't already also pull in like a huge runtime. So like really the only two languages you can compile properly right now is C++ and WASM and Rust.
Mm-hmm.
And so if you want a nice type-safe language, those two aren't really like really a TypeScript-ish thing. That's not gonna cut
how do you feel about Rust?
I love it for certain things.
Yeah, I'm very intrigued by it. It's got some novelty. I'm into novelty.
Yeah. It's also just very pleasant to work with because there's a bunch of people putting thought into UX, which is nice.
Right. So should we invite everybody back?
Let's pull them back.
So what do I do? Just close all the rooms and force them back in?
I think that works.
Okay, I'll just warn them.
Maybe we'll do a quick question round of if things worked or if things were very unclear.
Are we going to be in the same breakout rooms for the next parts?
Do you want to be?
Might be fine. So I think we were a good team. I was happy to work like that.
Yeah, it was pretty random the first time. It might be random again. I have no idea, but I'm happy to shuffle people around if you want to work with the same people again.
If it's really complicated, then it's fine. So it's just I couldn't set it up, and so I was a theorist.
Well, that's great. You know, if someone's driving, then not everybody has to be typing.
Yeah. I think it worked out.
I'm here to serve, so whatever the audience wants, I will do my best to provide.
Right, cool. I mean, that sounded like that was a successful group. I hope we had a few more of those.
So it looks like the breakout rooms are actually preserved, so I can like open them and close them at will, and they stay the same.
That's great. Was there any group where we didn't have anyone that was able to screenshot or drive? Should we split it up a little different?
They will have to report their own results.
Mm-hmm. In the room, everything went fine.
I feel like it would be useful to have someone in every group, ideally that knows Kotlin syntax.
Yes.
Because otherwise we all understand conceptually what to do, but we can't actually carry it out. But we'll get there. Our group's doing all right.
All right, that's good. I mean, I'll show you the solution for this. I'll ask one of you to tell me what to write, and then maybe we can get a bit more familiar with Kotlin syntax along the way. You don't need much syntax, so we should be good, I guess. Right, I think that sounded like positive results so far. So now I need a volunteer to help me implement the other few cases I need to make all of the literal and var cases type check.
If no one else
Can I
wants.
do it?
No?
Yeah,
Okay.
sure.
Go ahead.
Okay, so if the expression is a string, we just return monotype the string.
I mean, we can also let multiple people do things, right? We can.
Yeah.
So I'm just gonna keep on adding this to do down here until it. Okay, so if that's the case, then we're gonna return a monotype.
Monotype string.
Yes. Okay.
Basically the same for Boolean.
All right. I'm just gonna do a quick pause here. So there's this little squiggle over here. So the IDE lets me do a thing. So I'm gonna hit it.
Can we like use pattern matching to
Yes, we
shorten the
can.
code?
Yes. So step one is here. It says you can lift the return out of this if. So I'm going to do that. So I moved the return out. And then it still suggests a thing and tells me you can replace this if with a when. So I'm just going to do that. I'm going to remove these braces. All right. And so one thing we can do here in Kotlin is actually we can say, I'm going to delete this one. It's just going to make it a little easier. And I can just add all the remaining branches. All right. Cool. So let's go.
So
Does Kotlin tell you?
Boolean.
Sorry.
No, please ask questions. It's just all good.
Does Kotlin fail to? Does Kotlin give you an error if you're missing one of the cases?
Yes.
Oh, very good.
All right, other guy. Let's go.
So monotype that.
I think that was a bool. I'm just gonna run the tests while we're here. Seems like we're doing pretty well. I think we lost Adriel. Maybe someone else wants to continue. I can look at the next test that we need to make happen. So this one over here. I think Manuel wanted to give it a try.
You have to check whether your variable is in the environment. So you have to do env.get on. First, it was surprising for me to. I didn't know how to get the name, but fortunately, my colleague was a Kotlin expert, so could say that it's expert.name.
Yes. So once we did the pattern match over here, Kotlin basically like smart casts the type of this thing. That's how that works.
Yeah.
Right.
But this can fail,
Mm-hmm.
or this can not find something, and then you somehow need to catch that error, and then but throw an error.
All right. So I'm gonna say, okay, that's the result of the tie, maybe, right? But it's possible that this thing is not here, right? So what we're gonna say is, well, if that type is null, we're gonna throw an error.
Yeah.
All right. And I'm just gonna leave that empty for now. We can figure out what we need to put in there. All right. And otherwise, it should just be the type, right? Sorry for cutting you off. That was what you wanted me to do?
Yeah.
All right. So we have a bunch of squiggles. So I'm just going to let Kotlin tell me to do all of these things, basically. All right. So Kotlin actually has an operator for the from maybe thing. And then now I'm just assigning a variable and then immediately returning it, which means I can also say this. So this is just the from maybe, but Kotlin has an operator for it.
Yeah. And
it's kind of neat, right? And now the last thing is it says, well, the actual error was nothing, but I was supposed to say unknown variable x. So let's do that. And Kotlin has a little bit of interpolation syntax for strings like so. Okay. So if I run that one more time, now all the tests pass. I hope some or most of you got this far. The first one is definitely the trickiest one because it involves setting up everything and getting used to all the setup and the tests and all these things, right? Let's see if the next one is going to be a little easier. So I'm going to look into let's, I think. Let's see, I have, yes. So the next one is let bindings, which I'm going to be doing. And so really the main thing here is, well, lets are used to introduce new variables, right? So let's look at what a let expression looks like in our language. So we had a let and we have a variable. And we say that that variable is equal to an expression, which is a terrible name, in somebody. Now, if anyone has a good idea for how I can name this expression, I'd be really happy, but I can't think of one. So it's just going to stay as expr. Okay. So now the question is, what is the type of that expression? Well, let's look at an example really, just to get started. And the example we had was let x equals 10. And how about I'm just going to say let x equals 10 in true. Can anyone tell me what that expression evaluates to if I were to evaluate this? Sorry?
A Boolean.
A Boolean. That's the type. Can you tell me what this thing
True.
evaluates to? It's just
True.
going to return true, right? Okay, so we're just ignoring the x here, and we're just returning this thing over here. And as you already said, this has type bool. Okay, and so that means that this thing up here also has the type bool. Okay, and the reason for that is something we call preservation. So evaluating an expression does not change its type in our type system, okay? So if I have an expression E with a type T, and evaluating E yields E prime, then I can conclude that E prime also has the type T. Okay, and this is called preservation. Okay. And so really what the whole thing, the type of this whole thing was the type of the body here. Okay. So let's try to implement that and see how far we get basically. So what I just said is that I somehow need to get my hands on the type of the body, and then I'm just going to return that. So the body is an expression. And how do we get the type of an expression? Any ideas?
We just call infer.
Exactly. We call infer again. And we're just going to give the environment we have lying around. So we're just going to use that. And then I'm going to say, I want to infer the type of the body. Okay. And what I'm going to do here is I'm going to pick the tests for the let. And let's just see how far we can get with that. So we can already see that a few of these things seem to be good, seem to be green. So let's try to find the first one in here that is failing. Okay, so this is the first test, and it just assigned x, assigned 42 to x, and then returned string, and that's kind of the case we looked at on the whiteboard, and we can see that that returns string, which works just fine. And now the next example is where we're actually making use of what let is used for, right? We're binding x, we're binding the variable x to the value of 42. We're binding the value 42 to the variable x. That's what how we say that. And then the whole expression is supposed to return, have type int, right? Because this whole expression reduces to 42. Okay. And what do we get instead? Well, we get unknown variable x. Okay. Does that make sense? Why that
Yes.
happens?
Yes.
We can put a breakpoint in here actually, and we can try and see what happens. All right. So we're in here. This is our expression. There's the expression that we're binding to x is 42, and the body is just a variable x. And so we should come around here, right, when we keep going. And the important bit is that the environment here has the size 0. There's no value in there. And then I'm going to have it continue. And we can see that we're looking for the name x, but the environment is empty. So what do we need to do? Well, the first thing is we need to change our rules, because that's obviously not the only thing that is happening here, right? So if we want to show that this expression has the type of body, and again, we're going to need the environment here because that's the thing we're going to need to be modifying, right? Well, there's also this expression over here, and we're going to say that that thing has type expr. Okay, so we're going to say expression has type expr. And then we're going to infer the type of body, as we already said. So body has type body. But we're allowed to use the variable x while we're inferring the body. Right? And the way we're going to do that is we're going to say, well, we're going to extend the environment and say, well, x has type expr. Oh, that looks terrible. Sorry. Let me get some more space in here. And we can maybe do this a little nicer. So we're going to say, well, we have the original context, but we're also going to add a binding to x at type expr. Right? And in that context, we want body to have the type body. Does that make sense?
Yes.
Great. If there's any questions, please don't hesitate to ask. So how do we go about implementing that? Well, we just saw there was this expert thing going on, and we needed that before we could start implementing, inferring the type of body. So let's say expert is, well, we're inferring, and here, as we look at our rule, okay, we're going to use the context that we got passed in when we try to infer the whole thing. Okay, so let's use that, and then we're going to infer expert.expert. Again, terrible name. If anyone can come up with a better one, that would be great. And then what we need is we need a new environment. Okay, and that's going to be the old environment, but we're going to be adding, and there's an extend function over here. We're going to be adding a new binding. Okay, we're going to say, well, we're going to bind the variable we're binding, as we say over here, x, right? That is the binder down here, and we're going to bind it to the type of expr. And then we're going to use that new environment to infer the type of the body.
How about you call your expert.expert, you call it the head, because it's going to be the head of your new list, and it's also a head in the body.
The thing is that that's not a list, it's actually a hash map, right? So, oh, that extend function has a terrible type, I'm sorry. Well, you might want to make that change if you just didn't see what I just did. Basically, you need to rewrap. So the environment is a new type around a persistent map. So this is a data type, which is like a hash map, but it's not mutable. And there's an extend function here, but I forgot to rewrap it. So if that trips you up, try to remember to rewrap the result inside the environment new type constructor here, okay?
Quick question.
Yes.
So it seems like most of the type inference is done purely through updating the environment and threading a new environment through each expression. Is that the case? And if so, does that change as soon as polymorphism enters the room?
Well, it's so as soon as okay, so it's true and false. So as soon as the polymorphism enters the room, the way you deal with environments changes. Yes, very much. But the main part, or like the main algorithm that we want to get to, or the focus point, is really unification and not threading around the environments. But we'll get to that in just a bit, basically.
Okay.
All right. Cool. So, well, that looks like a very faithful implementation of what this thing does.
Christoph, can I ask a question?
Yes, you can.
I've only been able to pay like 80% attention, unfortunately. Could you just walk me through quickly how this, what you've written here on the whiteboard relates to the code, like one piece of it at a time?
Let's do that. Okay, so the way we're reading this notation, really, right? There's this long line. So everything below the line is the thing we're trying to show, and everything above the line is what we need to show in order for that to be true. This is like a proof notation usually, but we're using it. Okay, so this is what we're trying to show initially, and these are all the subtasks we get from doing that. Okay, so if we want to show that for an expression, for a let expression which binds a variable x to a variable to an expression called expo in body, we need to infer the type of the expression to be tyexpr. That's what we're doing here. Oops, over here, right? And the input to the inference algorithm is this environment as well as the expression, and we're using the same environment for to infer the expr up here that we got initially, right? So we're just passing that in here, and then what we get back is the type of that expression, which is called tyexpr. And then the second thing we need to do is we need to do this part. And what we can see here is that we have the original environment and we extended with a binding of from x to type tyexpr. Okay, and that's what we do over here. So we take the old existing environment and we extend it with another binding. Okay, remember the environments are mappings from variable names to their types. Okay, and then we can infer the type of type body by calling infer over here using that new environment we just created and passing in the body expression. Okay, and the thing we wanted to show all along was that the whole thing then has this type, right? And that's why we return that type over here. Now I'm going to run the tests and hope that everything passes. And that looks good.
Can I ask a question?
Yes, sure. But you've got horrible feedback going on.
What about evaluating the expression because we are using for example, if there would be some more complex expression, we're finding it. So, and don't we need to evaluate it?
Well, part of the reason we do type checking is that we kind of want to figure out if evaluation is going to work out before we start evaluating. So if we had to evaluate in order to type check, that would be a little sad. Really, the idea of inferring the types of these things like this is that we can recurse and break these, like infer these like more complex expressions by breaking them down into their smaller parts without having to evaluate, because as we said before, this language isn't total, so we have recursion, right? So evaluation might not terminate. So you really don't want to evaluate during type checking, if possible, or you want to keep it to a minimum for certain languages.
Okay, sure, thanks.
Does that make sense? Maybe it doesn't. Maybe we can get into it a bit more later on. All right. So I hope this kind of made sense. I basically took the rule and I kind of faithfully implemented it as written. And that seems to make the tests pass. Now your next task is going to be dealing with lambdas. Lambdas are very similar to lets. Okay, and we're going to write down the rule, or we're going to think about what the type, how we're going to go about inferring lambdas before I let every one of you go into your rooms. So let's start out by looking at what type we want to infer. So a lambda syntactically looks like this, right? We have an X and a body. And X is a name, and body is an expression again, okay? And well, really, let's think about what the type of that is. So what if I gave you, what if I told you, what's the type of X to, well, let's start with this one. If X, then 10, else 20. Can you come up with a type for that expression and maybe explain to me how you got to that type?
From Boolean to number.
All right, so this is a function type, right?
Yeah.
From Boolean to, and well, numbers are ints in our system. Okay, can you explain to me how you got there?
So I saw X is used in an if expression and the condition is to be a Boolean. So then we know the argument of the function needs to be a Boolean too.
So the argument type of the function, this thing, is what corresponds to this variable, right? That's the type of the variable being bound in the function. Very good. And then how did you get to the int?
I know the condition needs to be a Boolean,
Mm-hmm.
and the condition is just X, so X must be a Boolean.
Your internet is cutting out. How did you get to the int?
Okay, sorry. So the condition needs to be a Boolean, so I know X is a Boolean. Can you hear me? Internet is
Yes,
dead.
you're kind of chopping up.
Okay, so one last time. I know X, the condition of the if expression needs to be a Boolean. So then we can conclude it's a Boolean too.
Right. But the thing I'm asking about is how did you get to that int?
What? Oh, I just saw the first branch is an int. So then the whole thing needs to be an int.
So that's the type of this expression really, right?
Yeah.
Yeah, that's the type of, that's where that int is coming from.
Yeah.
Okay.
Yeah.
And so what we can conclude from that, or what we should be able to conclude from that, is that every lambda, the type of every lambda is a function type. Okay. And every function type consists of the type of its argument and the type, and I'm going to call this type body, right? Because that's the type of the body of the lambda as we saw up here. Okay.
Yes.
Now, when we were looking at the type of the body, just like with the let, we were able to use the argument, right? The variable X was around, so we need to extend the environment again, and we're going to say X has the type tyarg, right? Because that's the type at which we're allowed to use X. Okay, and then, well, then we can show that the body has the type body. Okay, so if we compare this, does that make sense to everybody? Can we follow along? All right, looks good. Seems good. Yes, there's a question.
Yes, I think the argument might be neglected. So not sure if it must go from the type of the argument to the body.
So you're saying neglected. What would that? What kind of type would that be?
Const maybe. So how could you infer the type of const?
So
we're going to get to that.
Without polymorphism.
Let's see. I mean, we could just say well, if you don't tell me, well, basically here, how we found out the type of X at some point, right? And that's the main thing that I want to get to. Up here, right, when we compare this to what Let did, was we had some place to get the type of this TyExpert thing that we needed to insert into the environment, right? And the difference down here is there is no such thing. We don't know what the type of the argument is until we've inspected the body, or by the time we see like an argument that is applied to this function or something, right? And the way this is represented in the type checker is that we say there are unknown types that we don't know yet, that we're going to figure out at some point in the future. Okay. And so, as you said, if I neglect the argument, so let's say I had a function x to 10, what type do I give here? I don't know what type that x is. I just know the thing returns an int in the end. Okay. And so if we look into the type checker and look at our types again, there is one more constructor that we haven't used yet, which is the unknown. Okay, so these are unknown types, and we've just got, basically we're just numbering them by ints, right? So we just say unknown 1, unknown 2, unknown 3, and so forth. Okay. And one capability our type checker has is that there is a function called a fresh unknown, which gives you an unknown that has not been seen before, basically. There's like a variable that keeps counting up. So whenever you call fresh unknown, you get a type that has not been used before. And you can just use that to synthesize a type for the argument. Other than that, the implementation of this thing should be very similar to how we inferred the lambdas. So I'd say let's split up into groups again unless we have more questions. Let's split up into groups, and I think this should take somewhere maybe a little less than 10 minutes, but let's say 10 minutes, and then we can see each other again.
Okay, breakout room. So I think some people wanted to be moved around. Remind me who you are.
What do you mean by moved around?
A few people are running operating systems that are not compatible with what we are doing.
Oh, me, I mean.
Who? You can just type into chat.
Or maybe we could just split up people into groups, and then those that have trouble just stay in the general room and we'll fix them while the others are already solving stuff.
I think it was 3 people in the same group that wanted to be
All right.
split up, actually. So I'll just move. Oh, it's Jan. And I think I don't need to move Christoph. Okay, that looks reasonable. See how that works.
And they're off. All right, that's cool. I hope this time around it's clear what they're supposed to do, but I think so.
So a couple of rooms have people who haven't joined. I guess I can wait for them to do that or shuffle people around a bit more.
I'm just going to get another drink.
Go for it.
Thanks for that question, by the way. That was a very good point of like making sure I do the I show the parallels between the math and the code.
Yeah, I mean, I'm a pedagogue at heart. All of my questions are half I want to know and half I feel like other people might want to know.
That was very good. Thank you.
So I've read a lot about type theory, and it's I mean, this has been a particular challenge for me, like translating the type theory annotation into code.
Mm-hmm.
Like the code makes sense and the type theory makes sense, but sometimes understanding how you would go about implementing something isn't always clear to me, for sure.
Yeah, definitely. And I mean, the tricky part really is that there's also like this type theory notation. So the way I'm using the notation here, this is not the algorithmic one. So that's why I have to like hand wave a few things, and
Yep.
like the unknown is nowhere in this, like nowhere to be found in this math rule, right? You can write this as an algorithmic one, which does include the unknown, but then it becomes really large.
Yeah, I mean, I came at this stuff from a very naive place, right? Having had no formal education or training in these concepts, and then like, where do you start? You kind of just jump in and wade your way through books and papers and talk to people.
Yeah,
I'm sure at one point I was thinking to myself, how do I implement a turnstile?
Yep.
But eventually, you know, you get the idea of an environment and what that means, like in an abstract kind of sense, and it makes sense. And then you can sort of think about types as just another form of value, but in a kind of different world.
Yeah, definitely. And I mean, I think coming at it from the way I did it with my students is I built the interpreter first, which also has a concept of an environment, right? At runtime, these variables exist, just that they're not bound to types, but to other values to be substituted later, essentially, as you go down the expression tree. And that helps when you try to explain why that environment exists during type checking as well.
So did you ever have to implement a compiler from scratch, like a toy compiler, as part of your education?
No, never. Which is, I think, is kind of sad, which is why I'm doing the compiler course now.
Okay. So do you know, is it typical when you do that, that you would actually implement memory management as part of it?
I'm not going to say typical. I think it very much depends on what kind of a language you're building, right? So there's, like introductory compiler courses, I think, stop at interpretation. If you want to do actual memory management, like allocate and think of memory layouts for these things during runtime, that's more of an advanced compiler course thing, I think.
Okay. So you're really just learning like syntactical idiom or something. Because I'm wondering if actually functional languages are much better for learning this topic than alternatives.
I mean, we're using Kotlin in a very functional way. You do need some state, basically. All the compilers in the world have some state. But yeah, usually the functional notation is a little easier. The most important features that you have type checking, and you have not type checking. Sorry, you need pattern matching, and you need some of the higher order stuff, usually for functions like map, filter, and folds. If your language does that, you're good for compiling, essentially. So most, like the MLs are really good languages for building a compiler. The schemes, if you don't care about types, are usually used in these introductory courses. C is terrible for it, and Java is kind of bad as well.
Yeah, I mean, they're not really fit for the purpose.
Yeah. Basically, I mean, that's why Kotlin is actually kind of ideal, I feel like. For one, because all my students have a mandatory Kotlin in the second semester, but also because it's kind of a familiar language. It's got really good IDE support in the sense that you hit dot on something, you just type something, you hit dot, and it shows you everything you can do, essentially, which is good for a beginner. But then still it has lambdas, so first class functions, and all the map and fold and filter stuff if you wanted. And it's got pattern matching with exhaustivity checking, which is important. So
yeah, it's a cool like material to work with, because if you're doing functional programming, a lot of it just feels like you're implementing it in itself. the sort of programming from nothing idea. I know there are some compiler courses where you're more or less creating like a mock object-oriented programming language, and then you're just designing to a specification.
Mm-hmm. I mean, there's also the ones that start with assembly, right? And then you build up a little bit more than, you don't get much further than having a few procedures and control flow, which is the other side of things.
Yeah, I mean, I think that's super valuable to know about that stuff. I don't know if I'd want to do it as a hobby.
At some point, you're forced into it if you want to do the functional stuff as a hobby, and the compiling stuff. Compiling functional languages at some point also becomes about control flow.
Yeah, you have to look for efficiencies. How much?
Mm-hmm.
Go ahead.
I think it's just really interesting how these things are, like how they. I mean, control flow in the functional setting is usually expressed as continuation passing style. So there's like these parallels, and you can convert back and forth and find like certain things are nicer to express in one way and others in the other way. So you get these like isomorphisms, and you jump back and forth, which is really nice.
Write an article.
Oh, all of those articles have been written 20 years ago. It's just people need to start reading them.
20 years ago,
20?
or
I mean 30
50,
to 40.
Yeah, maybe 50 years ago. So I'm finding I'm getting to the age when I say 20 years ago, I really mean 20 years ago, starting in the year 2000.
Exactly, that's what I thought about, but it wasn't. I was very like, I didn't mean I meant the 1980s, the early 1990s, maybe.
Yeah, like my first notion of a long time ago is like the 70s.
I wasn't around then, but
I was barely around then, but that's why it's my idea of a long time ago.
Yeah, the book I'm reading right now was written when I was born. Was printed when I was born.
Which book?
Compiling with Continuations.
I don't know this one.
I wouldn't recommend it as like a light reading. It's a very special, like it's a specialized topic, but like every paper that was written after it about the topic refers to the book. So I figured I'd read the book first.
Cool. So how much longer should we allow people to linger in their rooms?
I mean, some of them came back. How did it go?
Shall I close the rooms? It'll give them one more minute.
Let's announce that we're going to close it, and then maybe.
Okay.
They'll get a sense of urgency and finish, or we'll just pull them back.
That's right when I click on the button, it gives them a 60-second warning to come back.
All right, that's good. People are coming back.
Sound test? Just wondering.
Hello, Simon. We can hear you.
Okay, weird. Somebody just told me the breakout room they couldn't hear me, so I don't know.
I mean, I can hear you just fine.
Simon, how's your quarantine going?
Pretty locked down.
You're in Berlin, right?
Yeah. Few streets over still.
Yeah. Bitte Abstand, bitte Abstand.
I got my official mask a week or two back.
Official?
The official one?
The ones they handed out.
Who's
they
that?
handed out ones?
Yeah, the city of Berlin handed out like a few 10,000 masks or so.
Oh, I had no idea. I just bought some handmade ones.
That's also fine. The one I have is a tiny bit fancier in terms of, it's an FFP2. You should probably hand wash it. I just have to figure out how to properly disinfect it.
Not that anybody in Berlin is wearing masks.
Yeah, it's kind of a problem. I mean, at the supermarkets, they are wearing masks, but otherwise a bit less so.
We're back now.
All right.
It's very hard to tell Berliners what to do. All right, Christoph.
All right. Looks like we're back. How did the groups go? Did you figure it out? Did you get everything green?
We nearly got one. We nearly got everything green, but we were missing the one with the several type variables. I think we just would have needed a minute or so more.
All right. Well, we can figure that out together then. I'm not gonna tell you, like, I'm not gonna do anything basically, and you're gonna figure it out for me. So I hope the other groups went well as well. And I'd say let's start here. So who'd like to give me an idea of what I should fix? What I could write, maybe.
I basically started out by copy pasting the let part, which works out pretty far.
Interesting. All right.
Then I guess replace the first expert because it simply doesn't exist there with a, how's I called again? Unknown something. Fresh unknown.
So this part?
Not the infer part, but only the part that's actually not
this
existing.
part?
Yep.
Well, that's going to give you a type error because infer infers the type of expressions. And
well then, okay, then your suggestion works better probably.
Yeah, I shouldn't have suggested it, I guess. Sorry.
And run this and see what happens.
All right, let's see what happens. Okay, so that gives us a few failed tests. I'm going to go in here and I find the first one that actually fails. This one. Which is, let's just run this one. Okay, so that thing was inferred to have type int, but it was supposed to have type u1 goes to int.
Well, you should definitely return a function type in the end. So you should have fun monotype function of argument and body, and then.
Mm-hmm. Okay, so we need a type of argument here. I'm going to call that tyarc, right? Because in the drawing I called that tyarc, and that was the thing up here. I'm gonna delete all of this stuff maybe. I'm going to delete all of this really. Oh, so we just have the tyarc. So the thing we need to get at now is the tie body. So how do we get at that?
That was nearly right.
Yeah, but I didn't want. Okay, so what do we do? Manuel, Tulligan, let's go.
Okay,
Sorry.
You go to line 51, 52 and copy those and put them there. And then
what goes here?
Tyarc. So you have to basically to type check the body, you have to extend it by the new variable that you've just bound, and that's this.
Mm-hmm.
And the difficult thing, so that gets you quite far, but then the difficult thing is what type will tyarc be, because right now it's just always unknowns.
Well, to me it looks like all of these type check now.
Oh, okay. So maybe that was the error, because we tried to look up this thing in the environment,
mm-hmm.
like in the variable rule, but that was wrong then, I guess. Okay, so next thing is unification that resolves those unknown or what.
Can you explain how this typearc will change? For example, you show this x that would be bool, but we are assigning it to unknown. So how does it change?
So far, we've only assigned it to unknown. That's because these are the only two cases in which we can figure out what one of these unknowns is. They're left for the end on purpose, because that's the tricky and fun part.
Oh, okay.
Well, some say the difficult part, but I'd say that's a mischaracterization. All right. So does that make sense? So this is what the rule was really. So this is just let, but because we don't have an expression that we can use to infer the type of the binder, we're just going to say, well, we don't know yet. We'll figure it out later. Okay. All right. So let me just look in our list. The next thing we're going to figure out is the substitution part. So what's the substitution? As you said, these unknowns, well, eventually we want to figure out what types go into these unknowns. And for that, we're going to use what's called a substitution. And the substitution is a mapping from ints, and those ints corresponds to our unknowns, and they map to the types that we figured out for those unknowns. Okay, so type checking in the way we do it is a constraint solving problem, and this is the solution for the set of constraints we'll figure out eventually. Okay, and so I have a few tests here. So the main function we need to implement here is apply. So as I said, a substitution is a mapping from numbers or unknowns to types. So let's say U1 corresponds to int, and let's say U2 corresponds to string. And you'll see this is a different error than the function error. So don't mistake this for a function error, right? This means U1 is should be substituted by int, right? So we figured out that the variable, the type variable, sorry, the unknown variable U1 should have actually been an int. And the last thing I'm going to put in here is U3, which is actually going to point at U1. Okay, so this is, at some point, we'll figure out a solution like this, and the operation I'm going to implement now, and let me show you all of these tests here really, is I am going to, starting with this substitution, which maps 1 to int, 2 to string, 3 to 1, and 4 to a more complicated type. And I'm going to apply that to other types. So what does that mean? Well, it means I want to, let's say I've figured out this solution for these variables, and I say, okay, I have and I'm going to call this thing S for substitution, right? And now I have an operation which applies a substitution to a type. So I say, let's apply S to the type int. Okay, and well, int is not going to change, right? There's no variables in int that we need to solve. Int is already fixed. But the more interesting case is when we say, well, what if we apply S to U1? Okay, and so we're going to apply all the knowledge we've collected so far, and that is just going to return int here. Okay, so we look up this unknown in the substitution, and if we find a match, we're going to return the match. Okay, so how about we just start there? So let's do that first. Okay, so what am I going to say? Well, I'm going to say we're probably going to need to pattern match on the type here. And I'm going to add all the remaining branches. Okay, and we said for all of these three cases, right, these are just the, these are the literal types here really. We're just going to return the type themselves because they don't contain any variables. So there's really nothing, nothing we can do here, we should do here. Right, and if I run that, that should get me as far as getting the first test to be green. All right. So what's the next test here? Okay, so we say if we look up a type, if we apply the substitution to an unknown, and that unknown exists in the substitution, it replaces it with the type that we look up. So how about you tell me how I'm going to implement that case, because that is going, oops, that was not intentional. That is going to be this case. I'm just going to move that up here. Oh my. I thought I knew the binding for these things, but apparently I don't. Oh, that's what it is. Okay, sorry. So what am I going to do here?
We're going to look into the hash map if the integer that you can get out of tie exists,
yes,
apparently. And probably you're going to recurse. And whatever is in there, you're going to do apply on that again. Well, if it doesn't exist, you keep the unknown that you just had. So it's again tie.
All right.
But
I'm just gonna go with that for now because I have a feeling that that's going to fix the test we're trying to fix right now.
Okay, so that basically you could later then recurse on that, but that's sort of one reduction step Or
Right. So this makes, so let's see how many tests we're passing now. So that's that's a really good start, right? Because we've now, as you can see, this one is green, this one is green. All right, let's do this one first. Let's do these tests in order. So this one says applying a substitution to a function type applies it to both its argument and result type. Okay, what does that mean? Well, okay, so let's try to apply the substitution here to the type U1 goes to U2. What would you expect that to return?
into string.
From int to a string.
Int to
Function
string.
type.
Right, exactly. Really, so what we found out here is that S of T1 applied to T2 is actually the same as S of T1 goes to S of T2, right? So let's implement that one. Volunteers? If we don't have any, that's fine. I'm going to do it. So what we have here is another, so this is going to return another function type, really, right? As we see here down here, if we are applying a substitution to a function type, we're going to return another function type, but we're going to recurse into the argument type and the result type here. Okay. And if I run that again, we get pretty far. And then we get to the last, to this test, which is, that's the point you were mentioning before, Manuel, right? So applying a substitution works transitively, so it finds a fixed point. So the idea here is that if I go in here and I say, well, what's the substitution applied to U3? Well, that's not just going to be U1, and instead that's going to be int. Okay, so what it does is it finds the U1 over here, and then it keeps looking up if we have found any solutions for U1 so far. Okay, and well, now I'm going to throw more Kotlin syntax at you. But basically, if this lookup works, and don't worry about the syntax, it starts to look like Perl, but I'm just going to write this down anyway. And basically what we're going to do is we're going to say, if the lookup worked, we're going to apply again. And if it didn't, we're just going to return the type. Again, you can write this out in like some lengthy if statements, but
Why can't you just apply to it like as a new function?
out of here,
Mm-hmm.
because that's going to recur forever if the unknown is not inside the hash map. Something seems to not have worked.
To the inner part.
Sorry.
To just to just that part.
This part?
Yeah.
Because that's an option, right? That's not always there.
Oh, okay. So basically, you're using it like a functor here or something.
Yeah, exactly. This is like a from maybe. Thing.
Yeah. Okay. So in Rust it would be .map, and then Haskell would be .map.
It would be in. Something's going wrong, and I'm doing stupid things. I'm sorry right now. Just like so. Okay, sorry. So yeah, so in Rust this would be, I think it's called or else. The function
Takes an option and applies a function to the inner part.
let me. So in Haskell, this function is called maybe. Okay, so it takes a value of type A and a function from B to A, and then you give it a maybe of B, and it gives you back an A.
All right. Yes.
Right. So this is like either it returns you this default, or it applies this function in here if it's a just and unwraps it for you. Right. So that's the kind of thing going on here. But
yeah. You do both at once.
Yeah, and then Kotlin has this Perly syntax for it, which, I mean, it's not pretty, but it works. So I'm just going to leave it in there.
What would happen if, maybe you've answered that, so I had to leave for a short moment, if the hash map points an 1, for example, to unknown 1 again? So if the hash map itself contains a loop, is that not allowed, or is it somehow
That is verboten, and we'll see why in a second.
verboten?
Very good, sharp thinking. You'll run into that when you try to build this solution. So that's a good point. Okay, so this is the part that I built, and now that we have a possible like a data structure that can hold a solution to a problem that we don't know yet, now we're going to actually learn to know the problem, and you're going to implement the algorithm for it. And that algorithm is called unification. Okay. And unification, I'm going to use the squiggly for it as this is the squiggly equals, that's unification. Okay. And so what unification does is, if I have a type T1 and I unify it with a type T2, that gives me back a substitution. And that substitution is so that if I apply it to T1, the type I get back, and notice that this is not squiggly, is exactly equal to T2, to S applied to T2. Okay. And those S's, that's the substitution that we're trying to figure out. And I'm going to give you a couple of examples, and we're going to work through them, and then you're going to implement that algorithm. So step 1, what substitution do you need to make these two types equal? Well, that's boring. That's just the empty one. Okay. And I'm not going to bother writing down strings and bools and stuff. How do you make these two types equal? Any suggestions?
Can I map 1 to string?
Exactly. So let's get into the more tricky cases. What about this one?
So I got two choices. You could map 2 to 1 or 1 to 2, but you should probably fix an ordering and always go upwards or always go downwards, something.
Exactly. Both of these are just fine, right? I can assign these in both directions, and that's fine. I should pick one, you're right. But it's not actually important that I pick one in this case. So this case, the ordering, it's fine either way. I think the solution, like the test, will make sure that you pick one particular order. But the reason why it doesn't matter which order you pick this is because unification is commutative. Okay. So so T1 unified with T2 is exactly the same as T2 unified with T1.
But I mean, left-hand side, right-hand side, I mean, you should either increase the number in your mapping or decrease it.
Well, you could do that, but it doesn't actually matter. The ordering of these numbers is just to make sure they're distinct. There's no actual ordering in these. We can talk about it in a bit. I want to make sure that we have this last case so that you can get to implementing it because, well, it's getting a little late. We want to make sure we get to the fun part, right? So how do you make these two types equal? Any takers? If we don't have any, I'll say it. I'll spoil the result.
U1 needs to be a string and U2 needs to be an int.
Exactly. So this needs to be a string and this needs to be an int. Okay. And then I'll show you two more things. Let me do this one. Let's say we wanted to make that type equal to that type. How would that work?
Do we represent them by hash maps again, or?
Yeah, this is a
Yeah.
this is hash
Okay.
maps.
So each thing can only have one
Exactly.
entry. And then you could, for example, you could map U2 to U1 and U1 to int. But it's a bit arbitrary choice, so not sure what a good algorithm is to pick a choice here that doesn't work. That works.
I mean, really, those two are the same, right? If I say U1 is int and U2 is int, that's basically the same as saying U1 is int and U2 is U1. But you're right. Both of these are fine. I think they're both equal. I think they actually, in the math, they actually represent the exact same thing. Okay, and the last thing I'm going to show you is this one, just to, well, no, maybe you'll run into these into the unit tests yourself. I think the unit tests cover these cases, really. The function you're going to be implementing is, and oh, you might need this one, right? So what I'm going to do is I'm going to commit this, all I have here, so that you can eventually potentially pull this from the repository. And God damn it. So you can use this as the basis on where of where to start, so you don't have to re-implement the substitution. If you already did, that's fine, then you're good. But otherwise, just pull from master. And the thing you're going to implement is the unification function, or the unify over here. And I've already put in this the bit over here, this zonk function, which really this just applies the type. This just applies the substitution that we're storing inside the type checker. So the substitution, unlike the environment, is a mutable variable. We just keep accumulating and more information in it. So that's why we're using like a Java hash map here, which is a mutable data structure, as opposed to the environment. Okay, and zonk just takes a given type and it applies to the substitution that we currently know of. And the function you're supposed to be implementing here is this unify function. So I wish you the best of luck. This is the most complicated one. So maybe let's say we're gonna let's do another 10 minutes, maybe 15. I'll ask how we're doing, and then I'll implement the rest in a mob programming style, because I think we're running kind of late here.
How would you like to do this?
So let's put people into their rooms for this one. This is the meat, basically. If they can, I'd like them to try and figure this one out, and then I'm going to do the rest in a
Give
more.
me 20 then.
Yes, 20 minutes. 10 minutes was short for the last one already.
Okay, I might have to do a little bit of shuffling. Oh, actually, we have somewhat fewer people.
Yeah, I mean, that's to be expected, I feel.
A bit of attrition.
As always. Okay. So we got 3, 4. Oh, Christoph's in all the breakout rooms.
Yeah, I've got the laptop on the side to have a grid view, but
All right, I'm going to open them now.
I mean, I could also move around and see if anyone has problems, but
Yeah, if you know how to do that.
no, I don't. Oh, I think only the host can. I can't assign myself to other rooms. Never mind.
You're a co-host.
Okay, maybe I can then.
You should have all the powers I have.
I'm gonna join my breakout room. But then I'd stop my sharing. Would that mess with the recording? I don't know.
Yeah. Maybe.
Is my second account also a co-host?
I guess not. I could make it one.
Because then I could try on the laptop and that wouldn't mess with the recording, I'm assuming.
Shouldn't. There you go.
All right.
Hope you know what you're doing.
Well, I don't, but that's fine.
You're playing with forces you cannot possibly understand when you mess with Zoom.
That's true. Okay, so I'm in a room now. Can I move around? Ah, I can spy on people. But this group is doing the thing, so that's good.
Are they just chatting about sports?
No. This is, I mean, I can't hear them, but I can see that they've opened the IDE and they're doing things, so that's good.
Okay.
So now I think I can join or jump around. So let's see what breakout room 1 is up to.
I should have thought to use 2 computers for this.
Okay, that group is also quite busy. They've got someone sharing and they're going at it, so that's good. Yeah, 2 computers is definitely a good thing when you're trying to. I mean, in general, even if you're just like presenting, because that way you can still view the participants and get a little bit of visual cues at least.
Yeah, noted.
All right, this group is also doing well. Loving it. And now the last one. How are we doing in room 5? All right, we've also got someone shared and there's stuff going on, so. Great, they're all going at it, so that's good.
So we give them another 15 minutes?
Yeah, let's do that. I know it's getting late and I know you probably don't want to stay forever.
Well, we have to get to the payoff.
Yeah. But it's unification, really. This is where to.
I'm here for unification.
That's good. That's good.
This is what I came to Germany for. This is what I came to Berlin for.
All right, that's cool.
You have a holiday for unification in Germany.
We have a holiday for a lot of things, yeah. Well.
So while we're waiting, tell us about yourself, Christoph.
I don't know. Not that much. Really, I could tell you how I got into the whole type checking thing and type theory stuff and why I kind of know how this works.
Yeah, tell us your origin story.
The reason for this is that Phil Freeman is the kindest person ever. And he took me up and taught me how to do all this stuff for my bachelor's thesis. So I had no clue how to read one of these typing rules until, well, he told me what book to buy. And then he explained how that worked to me. Because just from the book, there was no chance. I just understand it, I think.
Which book?
Types and Programming Languages, which is why it's now my favorite, like a book very dear to my heart, often abbreviated as TAPL, T-A-P-L.
Yeah, famous. Famously hard to read too, I think.
I'm not so sure about that. You need to skip the part where they do all the math.
That's the part that I didn't get through.
It's the second chapter where they introduce the mathy notation for how to do induction as a proof thing. But
you weren't. Did you have a formal academic relationship with him?
No, not at all.
He's like an industry programmer, right?
Yeah, but he built the PureScript compiler though, so that's primarily where I know him from, right? So he's the main author or the first author. And I built the IDE integration, and then I needed a topic for the bachelor's thesis, and that's where the type hole search is coming from. That was my bachelor's thesis.
That is a very useful part of PureScript.
It is indeed. I use it all the time when I'm doing PureScript. And he mentored me, and he even flew over from Los Angeles for my defense, if you could call that a defense for a bachelor's thesis, but for my presentation, basically.
That's pretty impressive.
It is. It is.
He must have seen something in you.
I think so, yeah. It must have been it. And like part of I was like, how can I mean, there's no way I could repay you. Like, how could I make it up to you? Essentially, he was like, just keep passing it on, essentially. So that's kind of what I'm doing.
Well, I think there are schemes now where you can get someone to invest in you and your future, and in return, you give them 10% of your future earnings for a specified amount of time.
Wow.
So you could do that.
It sounds like a pyramid scheme. How about those those people they're then teaching and investing in, do you get a cut of that as well?
I think you should. Makes sense to me.
Keep the snowball rolling.
Beats working for a living.
Yeah. I mean, but yeah, basically, so I totally get what you're saying. It's like there's this stuff you kind of need to. It's kind of hard to get started on it, right? Where do you find an entry point? And to me, I just found someone kind enough to show me.
Yeah, I mean, in a sense that is the classic model of how to get into anything, how to learn the art of anything, the art of functional programming in this case. Having a mentor is super important. You can certainly learn things in a more formal and rote fashion, like just going through the education system. I haven't met too many people who are successful doing that who aren't also really good at self-motivating and self-educating. And I think that they can sort of gain benefit from the academic system in spite of it, not because of it.
Yeah, that's not a bad way of thinking about it. Just saying, I'm just gonna put on the lights because I'm starting to get really dark here.
Sure.
That's a little hard on the eyes. Yeah, I'm not too convinced about the whole academic system thing.
Yeah, it's a much longer conversation. I mean, I think education is important. I'm a big believer in it, and to do it at scale, it has to be this way to some extent, although it's really the mentorship parts of it that have always been invaluable for me. I mean, you end up finding people like that inside that system if you're lucky.
Yeah.
You're very lucky to find someone outside that system. I think that's pretty unusual.
I mean, yeah, I found someone, but really I built the PureScript ID before that. So you need to, I invested a lot in there. Like the open source can give you these things, but you do need to kind of pour some of your youth into it, or like some of your life into it to I don't know. I think the biggest problem that we're having in academia in Germany is that it's scaled up so much because, well, not because, but part of that is because that it's free essentially, right? Everyone gets to go to university, which I think is a system worth preserving, but that also means that the entry classes are like 200 students per class, and it gets really hard to find someone mentoring you in that kind of a setting.
Never thought about it. I mean, classes in the US are also very big despite the cost of university.
Yeah, like I remember my Chem 1 class, there's probably like a good 200 people in that one, just like a giant auditorium.
Yep.
I mean, my graduating class was a little bit over 2,000 people. And that's the whole class, not any individual class.
Yeah, I mean, there's these like classes that the students get to select, like things they're interested in. Essentially, there's 2 of those in every bachelor like curriculum. You can pick 2. There's like 12 options or something. You can pick 2 out of them. My course is one of those, right? Students that are interested in the topic of programming languages and compilers can choose this one and get 5 credit points for it.
So you're doing this on the side?
Yeah.
And where?
Well, actually at the local university. I mean, it's all remote, right? Because Corona, but it would be a 10-minute bus ride if it wasn't. And that's like a side campus of the Cologne Technische Hochschule Köln, which is not the university, but the like applied sciences university one, Fachhochschule. I don't know if you know the distinction.
Not really.
Yeah, so they're supposed to be more praxis oriented. You can study there. You can get your degrees, but it's not they're more focused towards practical things rather than the theory and academia stuff, I guess.
That's where you're teaching?
Yeah, the one in Cologne, exactly. That's where I'm teaching, and really the only times I've found mentorship during my studies was in these classes, because they're kind of smaller and they're filled with people that are kind of like students have chosen these topics because they're interested in them. So you're more invested in it, I guess, and the teacher knows that they're working with people that are invested in these topics.
So how does this work? You teach once or twice a week in the evenings or something?
I teach once a week in the morning at 11 p.m. till 13 p.m.
Okay, so you just work your regular job like around that
Yeah, exactly.
time. That's really interesting. I miss being able to teach on a regular basis, and I keep thinking if it were possible, I should find a way to teach a course at one of the universities in Berlin.
And you'd probably, I mean, you're pretty good at it, I'm sure. You've got lots of experience, right? So
yeah, I mean, in English Lit, of course, not in any kind of computer science topic, because I kind of still want to keep like a hand in that world.
Mm-hmm.
I work all day on this one. I just figured I wouldn't be able to do it without a PhD.
I mean, I only have a bachelor's thesis, so that's probably not a requirement. You can't teach courses for people above your academic grade, essentially. But if you're,
I used to say I almost have a PhD, but like a PhD is like kind of a Boolean situation. Like,
all right,
there's no such thing as almost having a PhD.
Right. Is the postdoc before or after the PhD?
After.
After, right? Okay.
Postdoc is what you do when you can't get a job.
I see.
At least in the humanities. Maybe like sciences postdocs are a little bit more prestigious. I'm gonna stoke some controversy on the YouTube video.
Oh my. I mean, for example, I know that Sam Aaron during his postdoc built Sonic Pi, if you've ever heard of that.
Don't think so.
So like it's a system that you can use to make music, to make these like algorithmic music, so programming to make music.
Mm-hmm.
But its primary motivation is being used as a teaching tool for undergraduates, and like not just undergraduates, but also just like actual kids in like schools. Because it is like, I mean, making sound with code is just a very tight feedback loop, and it's like immediately useful to kids. And he's really passionate about that. And I think I think maybe it was good that he didn't find a job, I guess, then, if you say postdocs are for people without jobs, can't find one.
Yeah, I mean, I think universities are looking for any kind of temporary role that they can come up with. Mm-hmm. Adjunct professorships in America, I don't know what the equivalent is here. Postdocs are certainly one of them. So it's like a temporary research project or temporary role that you have. I mean, you can tell I'm like a little bit cynical about it.
Yeah.
There are certainly opportunities to be had. I mean, certainly having a postdoc is better than having nothing. And it can be a good bridge to a more permanent position. But again, like I'm not too familiar with how this works in the sciences. I mean, it may have been institutionalized at this point where you kind of have to do a postdoc in order to have the credibility to get like a tenured position somewhere.
Probably.
So
yeah, I think there's also this like huge pressure to publish papers.
Yeah, for sure there is. Right. And this varies country to country. It's pretty toxic in the UK, is my understanding. But
I mean, he's also from the UK, so yeah.
Yeah, for sure in the UK, I think it's pretty toxic from what I hear. In the US, I wouldn't exactly call it toxic. It's just enervating.
Yeah. Yeah, he talked to me about it. Like he's published a bunch of papers on the system, and it's like all kinds of theoretical things, and there's monads and all that stuff. But he doesn't care about any of that, really. He was just trying to build a system that he could use to do live coding and teach kids, and he had to write all these papers on the side to be able to keep doing it.
Yep. There's like some kind of minimum requirement of publication. You have to like show that you're working.
Yeah.
So we still have a few more minutes, and the last way I'm going to kill some time, I noticed that you have the same microphone that I have. I'm not actually using it right now. So Can you explain your audio setup? So you're using monitor headphones?
I'm using, no, I'm not using monitor headphones. I'm not monitoring my voice. This is,
Oh, you're not?
I mean, right.
Okay.
Maybe I should set that up possibly. This is, yeah, so the microphone, you need to plug it into an interface, right? It does, it's got like phantom voltage kind of thing, right?
I've got a mixer.
Yeah. I mean, I've got an interface thingy in between. So, but the output of this thing is XLR, right? The cable. Right?
Yep.
So yeah. So yeah, and that goes over there. And then I used to have it in the back, like somewhere behind the monitor, so it wouldn't be in my face all the time. But that created that horrible sound where the sound bouncing back off the wall was stronger than the stuff I was saying, like speaking in the direction of the microphone. And so, but since I've put it like right next to me, so that I can put it right in my face, the sound has become a lot better.
Maybe I should try it again. I was having a hard time not being able to hear myself, and sorry, not being able to hear the person speaking like in my ears.
Oh, did you have the monitoring set up for that?
Yeah.
Well, Joel, thank you. Have a
Hi,
great
Joel.
evening or day, wherever you're from.
He's in Pittsburgh.
All right, so great day then.
Yeah, so I had the monitor set up so I could hear myself, but I couldn't hear the other person I was recording with except from the computer.
Oh, right.
Which didn't seem quite right.
No, that doesn't sound right. Yeah, I want to, I mean, you can put both on the same headphone, right? Just.
Well, I'm not sure. The monitors are plugged directly into the mixer.
Oh, you did plug it directly in, and no, these are plugged into my PC, right? Yeah, okay, I see what.
Okay, so you're just using the microphone as just another
just the microphone
audio source. Okay.
Yeah, if I was recording something without simultaneously speaking to other people, I might set it up so that it would be monitoring. But then I'd be using streaming software probably if I was recording myself, and then I could just monitor via the machine as well, via the computer.
Yeah, I decided not to use the fancy mic for these because I tend not to talk all that much compared to the guest.
Yeah.
All right, I'm going to close the rooms. That will give them 1 more minute.
All right. Let's hope they got there. Yeah, I've been using this. Like I've bought it for streaming a whole some time ago, a couple of years, but I really got to put it to use now that I'm doing the online lectures, and I've also started using it just for meetings in the company because I think it's just having listened to recordings of myself. I think it's just a lot nicer to listen to someone with a good microphone than having the fan spin of the laptop in the background, which is.
Yeah, that's a good point. I mean, I never thought about using it for work meetings, but if you think it makes a difference, maybe I'll give it a shot.
I mean, it doesn't make a difference for yourself. It's the others that.
No, that's
benefit from it, right?
I mean, that's what I mean. There are advantages to being understood. I mean, not just the sound, but also being nicely lit, if you can manage it. How else do I make a first impression on people I've only ever met digitally?
That's true. That's true, actually. It's also just a lot more true to the actual sound of your voice.
Ah, we nearly got it. we just did the occurs check.
8 seconds.
Isn't that software in a nutshell? We nearly got there.
8 seconds to spare.
Nice. So it seems like that timing was all right. So I did do the thing where I jumped through all the rooms, and it seemed like everyone was sharing and everyone was programming, so that made me happy. So, all right, let's look at the solution. Really, does anyone want to dictate here? We need to move a little quickly, so I'll just type whatever you tell me to.
If they're both unknown, if they're both not unknown, you just have to check whether they're. You should check whether they're equal.
Can I just start with this?
Yeah. And then that's fine then. And okay, well, we can do the functions. If both are functions, you have to recurse into argument and result.
All right. If they're both are, if Taiwan is a function.
Yeah, if Taiwan is monotype function and Tai2 is monotype function, then you unify tie1.argument with tie2.argument.
That sounds great. Yes.
And then you unify tie1.result and tie2.result.
Mm-hmm.
And then you return, I guess. So maybe you don't need that. Okay. If one is unknown and the other one is not unknown, then you can just assign the not unknown one to this variable. Well, okay, so you look at, well, is tie2, so that's the occurs check, is tie2 a function from tie1 to tie1? In that case, you say, oh, occurs check, we can't do that.
It's actually a little different than that. Let's just do the non-occurs check version. Let's just do the happy path, and then we'll figure out what's okay.
Yeah, well, the happy path is you basically you add to your substitution map that you add tie1.u maps to, yeah. So I guess you have to do tie1.u is now tie2.
All right.
And you have to do the same for the other way around.
The other way around sounds good. So this is you, and this is tie1, right? Like so. And you said that gets us almost all the way there? The only thing missing here is the occurs check, right?
Yeah, so you have to check in. Okay.
So now I show you how to do the occurs check. So occurs, that occurs part means that does this unknown, so does tie1 occur in tie2? Okay. And I don't expect you to be able to fix the occurs check. That's just like a little, let's see if you can do it. But there's an unknowns function on these, right? So I can do, does tie2, the unknowns of tie2, do those contain tie1? And if so, I'm going to throw an exception, and I'm not sure if I'm not saying what, but what I'm supposed to be throwing, but I'm saying occurs check failed here. That should be good enough. And I need to do the same thing over here, just with the thingies flipped around. So I'm just going to do that and run this. Oh, wait, what am I doing wrong? tie.u, okay. And now all the tasks pass. And now I could it's possible to extract this out into a function and reduce a little bit of the duplication here, but I'm just going to leave it in there if that's fine. Okay. And so the important bit here is that now we have this unify function. So first, thank you very much for dictating this. So now we have the unify function, and the unify function lets us say that two types are equal. And that is going to allow us to implement our last two rules. So step one, let's do applications. So, well, I'm just going to say, if we're inferring the type of an application, we are going to have a function and an argument. And both of these are expressions, right? And I'm just going to say, the result of applying a function to an argument, I don't really know anything about that shape. I'm just going to call that type result. Okay. And then I'm going to say, well, the function, that's an expression, right? So I can infer its type. So I'm just going to say, well, function is going to have the type tie_fun. And then the argument, again, that's just an expression, so I can infer that. So the argument is going to have type tie_arg. And now I have these three types that seemingly don't have anything to do with one another. But I'm going to write them down here because there's one more thing we know. So we have these three types, and I've left a little bit of space between them. Can someone tell me what I need to put into these gaps? How do these three types relate to one another?
Do you want a substitution rule here, or that doesn't, or do you just want an equation of types?
So this is what I want an equation, right? So tyfun, there's a relation between these three, right?
Well, tyfun is a function type, and it should return a result, and it takes an argument.
Right. So these two tuples must be equal, right? Does that make sense? Tyfun is a function that takes a value of type ty argument and returns ty result. Okay, so when we're applying this function, we're giving it a value of type ty argument, and the return type is the type of result, and that's the type of the whole expression, right? Because the function application returns this type essentially when it's applied to the right argument. Okay, and so now let's write that down. So what do we have? We have these three types, and we have this equality. So let's just write that down in code, shall we? We have over here, we had a ty argument. Okay, and we got there by inferring the type of the argument expression. And we had a type tyfun, and we got that by saying we're going to infer the type of the function expression. And then we're going to say, well, ty result, we don't know yet. There's no expression that corresponds to that. So we're going to say that's a fresh unknown. But we already know that we're going to return the type ty res as the result of the whole thing. And now the last thing we need to use is this piece of information, right? Tyfun is equal to ty arg goes to ty res, right? And this whole making two types must be equal, that's exactly what the unify function did. So we're going to say tyfun must unify with a function type that takes ty arg to ty result. Okay. And now if I run the application tests, what you'll see is that they all pass because that's all we needed to do. Once the unification, which is the hard part, is in there, we can figure out all of these. Okay, and that actually lets us start solving some of these types. If we would just want to go back real quickly and look at the examples that we looked at before, and I'm gonna run these. You can see how many of these can we actually infer by now. So you can see it infers the int. Up here, it infers the type for all of these, really. Like the type checking fails before the execution is able to fail, right? So we can tell if a program is wrong before we need to execute it, essentially. And then the interesting bit is down here, the simple application, right? So here we can figure out the type string. So that must mean that we must have figured out the type of this x variable, right? And we can figure out the type of the const here, I believe. So that's this one, right? So if we apply the first argument, we can figure out that the return type of this thing is going to be an int because we apply an int over here, right? So this is unification at work. This is the algorithm you just implemented. And now the last bit is the if. And again, I'm saying it's kind of late, so I'm going to implement that for you, I'd say, unless, well, I guess if you want to implement this yourself, you kind of need to look away now, but I'm going to do it in front of everyone, I think, if that's fine with you. So let's just think about an if really quickly, and then we can see. So how do we infer the type of an if? Well, we've got three things, right? We've got a condition, we've got an expression I'm going to call T, and we've got an expression I'm going to call E for else. And the whole thing is going to have the type ty. And because there's nothing changing about the environment here, we're not binding any variables. I'm going to ignore the environment for now. So we have cond. And what type does cont need to have? Well, cont needs to have the type bool. Or if we're being more faithful to how we're going to implement this is going to have type tycond. And T is going to have type tythen. And E is going to have type tyelse. And again, there's a few things we know about these. So we know that tycond must be equal to bool. Right, exactly. So that must be equal to bool. Then, what must that be equal to?
else.
Else. And actually, these two must be equal to one more thing.
So the return type of the whole thing.
Exactly, that's this thing over here.
Ty.
Right? So let's code that. So I'm going to say tycond, what's that? That's the type of inferring the type of the condition here. Then, that's going to be the type of inferring the then case. Else, well, that's going to be the case of inferring the else case. And now let's do these equalities we figured out. So tycond has to unify with monotype.bool, right? Then has to unify with else. And now I could make a fresh unknown and unify that with either one of those, but I can just as well just say return then or else. It doesn't matter, right? I've made sure that they equal before. All right. Does that make sense to everyone? Any questions before I run the tests? All right, looks good. So let's run the tests for if. And that's all the tests. And if we look over here, that's all the stuff I wanted to show. There's a little bonus down here, but I think this meeting has gone long enough, this meetup. I'm going to commit this. I'm going to upload it. I'm going to push it to the repo all the way to if. And you are going to, I mean, if you want to, you can totally pull this down and figure out the tests for the recursive lets, right? And figure out how you're going to implement that. But I'm going to stop here because, yeah, again, it's kind of late. So thank you very much to everyone for participating and all the, well, yeah, really participating and telling me what to write down and all the nice group you did in the nice work you did in the groups, going around and seeing all of you sharing your screens and working in the IDE together was really nice. So I'm really glad we got this whole remote workshop thing going and working.
Yeah, and I think it's okay that we had a little bit of attrition. The people who stayed really worked on it, and this workshop will live forever on the internet, so other people can benefit from it. And this was super great. I mean, you showed how what I think is probably an intimidating concept for some people is really just a series of very basic substitution steps. Actually, it seems like type checking is so simple, every language should have it.
Yes.
I agree. Well, the thing is you kind of need to design your language in a way that makes it easy to type check.
Convenience excuse.
Yep.
So let's thank Christoph. You can say thank you in chat. You can wave your hands in the air. You can give him a clapping emoji.
Thanks to everyone for participating. And thank you so much, Stephen, for setting this up and moderating it.
Absolutely my pleasure. You're always welcome back.
This was awesome. Can you give a follow-up with the more complex type theories?
I mean, totally, we could, but my main worry is that during the next meetup, we'll have a few other people joining for the first time, and it's always kind of hard to. But I mean, yeah, we could do that. Maybe not at the, I mean, let's figure something out, I guess.